Okay, so last time and Delaney, you were gone last time. Who else was gone last time? Okay, so we went over quantum model and we mapped out how we would map out the structure, showing the arrangement of the electrons in their orbitals. Okay, that's what we did. Then we ended on talking about how we abbreviate that, because as we saw going over to neon, that the drawings were going to get very busy, and you wouldn't really be able to clearly show everything because it's going to get so busy. So we talked about two ways to abbreviate them. One was the orbital notation, showing the energy level in the orbital and the electrons with their spin numbers. And then we did an electron configuration abbreviation using an exponent to total up the number of electrons in the orbital. Abbreviation. So today, what we're going to do, we're going to do a little bit of reading, because we talked about here, S only had one space to put electrons, but then P had three spaces, X, Y, and Z, because they point in different directions, and that was that magnetic number component of the quantum number. And so, because they have three spaces, we kind of had the discussion, well, do we just start filling X, then Y, then Z, or do we do something else? And so we'll read about that today. And remember, the theme there was getting to the lowest possible energy state for that electron arrangement. And that was the ground state. And so what we'll look at today, we'll continue on that. We'll look at valence electrons and how we can see valence electrons and inner shell electrons using that abbreviation. Okay? So I think we're going to be on page, it's like 104. Get 104. Would anybody like to volunteer, or should I volunteer Drew? Ashley's gonna go? No. Oh, we vote Drew. Okay, Drew, would you like to start us off? Top of page 105, top of page 105, electron configurations.
The quantum model of the atom improves on the Bohr model because it describes the arrangements of electrons and atoms other than hydrogen. The arrangement of electrons is known as the atom's electron configuration. Because atoms of different elements have different numbers of electrons, a distinct electron configuration exists for the atoms of each element. Like all systems in nature, electrons and atoms tend to assume arrangements that have the lowest possible energies. The lowest energy arrangement of the electrons for each element is called the element's ground state electron configuration. A few simple rules combined with the quantum number relationships discussed in section 4.2 allow us to determine these ground state electron configurations.
Okay. So the lowest possible energy. So think back to when we looked at hydrogen. How do we know that electrons can have energy in their orbital?
Because of the photon they give off?
Yeah, because the photon they give off. Right? Electrons can absorb energy, they can move away from the nucleus, and then when they fall back down, they give off a photon of a particular energy. And so when the electron is in its lowest possible energy state and not giving off a photon, we call that it's the ground state. Okay? Let's go, Ashley.
The role of electron configurations for the ground state of any particular atom. First, the energy levels of the orbitals are determined. Then electrons are added to the orbitals one by one according to three basic rules. Remember that real atoms are not built up by adding protons and electrons one at a time. The first rule shows the order in which electrons occupy orbitals. According to the principle, an electron occupies the lowest energy orbital that can receive it. Figure 416 shows the atomic orbitals in order of increasing energy. The orbital with the lowest energy is the 1s orbital. In a ground state hydrogen atom, the electron is in this orbital. The 2s orbital is the next highest in energy, and then the 2p orbitals, beginning with the third main energy levels, and equals 3. The energies of the sublevels and different main energy levels begin to overlap.
Okay, so let's look at that diagram on 105 there. And we see, if we start at the very bottom at the lowest energy, what is that energy level? 1s. Okay. Then the next highest energy? 2s. And then the next highest energy? 2p. And we see how that works from these diagrams we did last time. All right. Then if we keep going, what is the next energy? So we have 1s, 2s, then 2p, then what? 3s, then
3p.
Okay, now don't follow the red line because this is, we got to look carefully. If we go up, who is the next actual energy level?
3d.
4s. Then 3d.
Okay.
Right? If you look at that diagram, right, 4s is just a little bit lower than 3d.
Oh, this one.
Okay? And then 4p. So, and we're going to, as we work through this today, we're going to see how that works. Okay? So it doesn't necessarily go 1s, 2s, 2p, 3s, 3p, 3d, like following those stair steps, which is kind of misleading. Really goes 1s, 2s, 2p, 3s, 3p, 4s, 3d. Okay? In terms of energy. Why energy? Because we want the lowest possible energy. And so all the work that's been done in figuring out like which orbitals have the lowest energy, well, it turns out that 4s is actually a lower energy than 3d. Huh? So we'll talk about that. Okay. All right. Ashley.
Now, in the figure, for example, the 4s sublevel is lower in energy than 3d sublevel. Therefore, the 4s orbital is still there before any electrons enter 3d orbital. Less energy is required for 2 electrons to pair up in the 4s orbital and for a single electron to occupy a 3d orbital. Also, 3d orbitals are fully occupied, which sublevel will be occupied.
Okay. So, our first rule, outbow. That's how you say it. Electrons fill the lowest possible energy. Okay. Tanya.
The second rule reflects the importance of the spin quantum number. According to the Pauli exclusion principle, no two electrons in the same atom can have the same set of 4 quantum numbers. The principle of angular momentum and magnetic quantum numbers specify the energy, shape, and orientation of an orbital. The two values of the spin quantum number allow 2 electrons of opposite spins to occupy the orbital.
Okay. So, next rule, Pauli exclusion.
Should we be writing this down?
Yeah, write this down. No two electrons can have the same quantum number. All right, so practically speaking, what does that look like? in our quantum model, we can assign that electron a number that describes the distance, the angular momentum, the magnetic number, and the spin of that electron. Okay? So, if we are going to assign this one a number, it is in the first energy level. What shape is the orbital that it takes?
Sphere.
A sphere. What is its magnetic number, or what direction is it pointing? 0, because spheres don't point in a direction. And then we drew an up arrow for its spin. We would assign that a +1/2. Okay? So that number describes that electron. 1s0 +1/2. Okay? Helium has 2 electrons. One of the electrons would have this number. 1s0 +1/2. That's that one.
What the
So
other 2s0 minus 1?
-1/2, yes, but it's still in the first energy level, so it would still be 1. It's in a sphere, it's in the S shape. It doesn't have a direction, but since it's spinning the opposite direction, then we say -1/2. Okay? So now, helium, the 2 electrons in helium would have this number and that number respectively. Different number, right?
Yeah.
And that's what Pauly said. Pauly said the 2 electrons can't have the same number. Pretty straightforward. In essence, you would not want to assign helium 2 electrons that were spinning in the same direction. Technically, they would have the same number. So that's what that looks like. So just always remember that in any energy level or in any orbital, they're going to be spinning in opposite directions. Okay. You don't really come across that one too often. Last one, Hund's rule. Lily.
The third rule requires placing as many unpaired electrons as possible in separate orbitals in the same sublevel. In this way, electron replacement is minimized so that the electron impedance happen once every time. According to Hund's rule, orbitals of equal energy are each occupied by one electron before any orbital is occupied by a second electron. And all electrons in similarly occupied orbitals must have the same spin. Applying this rule shows, for example, that one electron will enter each of the 3 orbitals in the main energy level before a second electron enters any of them. This is illustrated in figure 18. What is the maximum number of unpaired electrons in the sublevel?
All right. So this is what we were talking about before. When we have the S space with its 2 electrons, the 2s space with its 2 electrons, and then when we go to the 2p space, it had 3 spaces,
X, Y,
x, y, and z. Okay. Then we discussed the question: do they pair up first, or do we spread them out? Spread them out. So Hun said we have to spread them out. Before we pair them. Okay? So when we looked at boron, it would have its electron here. Carbon then would be in the next space. And what's next? Nitrogen would be in the next space.
then oxygen X would be.
And then oxygen would pair, and then fluorine, and then neon.
So after those are all full, then you would go
To 3.
3s,
Then you go 3s.
and then 3p, and then
3p, and then
4s.
4s.
And And then 3D.
3D. Yes. So, in terms of energy, right, the alternative that Hun talks about is that this is the alternative. We pair them up, and so we fill up X, then we fill up Y, and then we fill up Z. The problem is there's more like potential energy here. This is more unstable than this. Even though they're spinning in opposite directions, they're both negatively charged, so they still have a little bit of repulsion. So we want to spread them as far away from each other as we can before we start putting them close together.
Oh, yeah.
So, by convention, then we will always, as we do the P, D, and F orbitals, we'll want to spread them out before we pair them up. You'll see that. Okay. So then the next section, so any questions on those? The rules, so we want them to be in the lowest possible energy state.
Yes.
No two can have the same number, and we spread them out before we pair. Okay.
Great.
Last time we went over orbital notation. So orbital notation was giving the energy level and the direction that the electrons are spinning in each one. Are we good there? Do we have any questions?
When we get to 3D, there's 5 spaces. So would they be X, Y, Z, A, B?
So
Or
these have different numbers. And part of it has to do with P is easy because we are recognize this three-dimensional X, Y, Z axis.
is that 3D?
D is a little bit tricky. Hold that. Hold that. Hold that. Okay, so Bryn has this question about D. Okay? P, I think we all recognize the XYZ axis, the three-dimensional axis, because we've probably seen it in geometry or algebra. Unfortunately. Okay. So, but D is a little bit different. D and F are a little bit different. And part of it has to do with where they're at. I mean, if we think about the 0, 0, 0, right, the central axis being the nucleus, and then first energy level, second energy level, third, fourth, fifth, sixth, okay, as we move out, right, how much volume is in 1s? I mean, what would the volume of that ball be? Not very big. But if we get out here to 5 and 6, how big is the ball?
Bigger.
How big is the volume?
Bigger.
Big. Okay. All right, so think that, there's just more volume. Secondly, right, P, X, and Y, and Z, they're just like right along the axis. So if you have this orbital along the axis and this orbital along the axis, do they overlap right here at the nucleus? I mean, because they're kind of coming in, so they're close here. But if I'm talking about the 5th and 6th level out here, and the 5th and 6th and 7th level out here, like, what's here between them? Space, empty space. So D and F, they take up space in between the axis. So like on the 45-degree angle, and the 45-degree angle like out here. Okay? So once you get further away from the nucleus, then there's actually room out here. There's actually empty space out here that electrons can be in. So we don't give them X, Y, and Z. We give them like X1, Y2 kind of a number. And XZ. Right, so we give them like this, we give them a little bit different number to communicate that. But it's the space between spaces. Okay? What?
Wait, can I have one?
Oh, yeah, no problem. All right. So that's how that works. So we wouldn't call them X, Y, Z. You would give them another thing.
What is the other thing?
Something like that. Yes.
36.
I can bring up the thing.
Bring it up.
Actually, no.
Can we take the nap down? Yeah.
So go. Hey, Bryn. So if you want to see, turn back to page 103.
I get it from
Alright.
my boyfriend.
So if you look on 103, it goes through the 5 different d orbitals. Notice it's dx2y2, dxy, dyz, dxz, and dz2.
Do we have to use this?
Okay, so that's how those would be numbered.
Okay. Okay.
Alright. Okay. Alright, backing up. So, from what we worked on last time, doing this orbital notation,
Yes.
okay? Then doing the configuration, where we just show the energy level and how many electrons are there. You'll get it. Okay? Okay. What I'm gonna have you do, oh, and guess what? They're all done.
I'm ready. I'm like 8 hours. And I read
Take up a little bit.
And I put it away tonight. Ew. And I'm actually gonna pass.
So we're gonna do some practice. I'll leave these up
We have the problem.
for kind of a cheat.
Can we do it on the board?
Yeah, I thought that'd be good.
Oh. What are we even doing?
What are we even doing? What are we
It's what we
even
did
doing?
last time.
Okay, so, let's see. We'll do carbon. How many electrons does carbon have? 6. Very good.
Yes.
What's your carbon?
There you go, twin.
Okay, let's go with,
Nitrogen. I thought it's my twin.
you wanna do oxygen?
Oh, I said nitrogen, but sure.
Oh, nitrogen?
I'll do either.
How many electrons does nitrogen have?
7.
Yeah, go like 2 or 3 at one, work together. Let's go magnesium. How many electrons? 12. Who wants to do that one?
Me.
Oh. I thought you were gonna hit you guys in the head with that.
Okay, let's go silicon
Further, it'll be really hard.
with 14. And let's do potassium. With
19.
Wait, so what are we?
Okay, here's what I want you to do. You only need to draw the picture if you need to,
Should I just put a P?
but just do the notation, the orbital notation with the arrows, and the configuration with the exponent.
Family reunion set.
I remember this.
You remember?
So it's like
Whoa!
1 S.
That's a good beat. Get it back here.
Whoa.
It's S1. S1.
No, it's 1 S. Yeah, it's 1 S. Yeah, it's 1 S.
And then with the little line thingy above it, just above.
You mean hello?
Above. No, like,
There's a camera.
Yeah, what's your gun for?
yeah. And then
XYZ.
the little up and down arrows. Like.
Come on, I did do that right.
You right.
Wait, how you get it?
No, I didn't.
Star.
2S.
What's the XYZ? What?
No,
The
you don't have
XYZ.
to.
Guys,
No.
that's the picture.
So, should I make them
With the arrows.
And then X,
How many
Y,
is
Z.
this?
Don't forget the X, Y, Z.
How many more do we need?
We need 19.
Up, down,
And then-
down,
So instead of
up,
showing
down,
arrows,
X, Y, Z.
How do you know?
Whoa, whoa, look at that, that's crazy.
Yep, that's right.
And then the little line.
Or sorry.
How do you do that without down?
Oh.
Oh, wait, time out.
How many electrons? are there?
Is it X, Y,
Are
Z?
you pissing us up here?
Wait, one second.
So you just have to remember that he has three spaces.
What's the P stand?
Shaving yourself.
It's the other shape.
Think you good?
Stop.
Okay,
I
try.
don't wanna hear any of you guys
calcium.
talk.
Like so.
I never said anything.
And then that one is one of the goofy guys.
Oh, yeah. It's kind of hard.
All right, so magnesium at 12, so you have 1, 2, 3, 4, 5, 6, 7, 8.
Yeah.
20.
And then we go the X, Y, Z.
And we're done.
Okay, I did all of that, guys.
7.
This
Yeah,
is
1, 2, 4, 5, 6, 7.
I'm just gonna guess.
And now, how do you do the
Wait.
the configuration?
What is that? 1, 2, 3, 4. We only need 9 more. Wait, what's after 2 P's? 3 P? I mean 3 S?
Like that.
Or down circle.
Oh, there's
not
not
in here.
Okay, so we would go to
So,
3D.
Am I right?
magnesium is 20
No, B, 3D, right?
Yeah.
No. The first electrons start in the S1, and there's 2. That's
Okay.
full, so you go to S2. There's 2 of them.
No, I was
And
thinking
then you gotta go to P, which has 3 spaces, a vertical space, a horizontal space, a Z space. And each one of those are gonna have 2 electrons as well, so 6 total.
Oh my god, which one was that?
Like each of those.
Each of the like little propeller shapes.
Oh, girl.
And what's like the up and downs?
Those are the electrons, so an electron spinning
Okay.
clockwise.
Oh, really?
is vertical.
Okay.
Because in each station you have 2 of those.
And so it's
One S, 2S.
Bruh, leave me alone.
Like this.
And you just
Oh, I forget that this is
my office.
But because you get, you're gonna have
No, you are not.
electrons
You
with
are
70, 80, 90, 100 electrons. So it's interesting.
What is it?
That's like the axis.
Yeah, so it's
X and Y.
X and Y and Z axis.
Where's the book?
So 1, 2,
taking- sorry.
Yeah.
And it goes 1 S, 2 S, 4 S1, and potassium is in. Not S1. Right?
Wait, what?
Potassium is the first one
Yeah.
in
Wow.
S.
But I think it's
It's the second one.
Okay.
Okay. So, what's the other thing we have?
Now I need to draw grid. No, get out of my way.
Okay, hold for just a second. Erase extra pictures.
Oh. No.
Gosh, I have a red.
I think I understand now.
Okay, so step back just quickly because I want to talk about something. I know, but then I can't show what I should. All right, so we'll actually start here. Actually, no. Here's what I'm gonna do. All right, I'm gonna do scandium because they got calcium, and I'm gonna do scandium. All right. Scandium has how many electrons? 21. 21. Okay. And it starts where?
Right after that.
Okay. And everything we do has to be full up to until we get close.
This one?
Right? So 1s2, that's covers our first 2. Then we go our full, we go to the second level, that's 2s. Then after beryllium, we jump over to boron, which is where?
5. In the
P block. So 2p. And how many can we have in P?
6.
6. Right, so S can have 2, P can have 6. After 2p6, after neon,
3s.
3s2.
Yeah.
Then
3p.
3p, how many?
6.
Because we're getting close.
4.
And then 4s2. Okay, now we're to calcium.
3d.
Now, scandium is the next one, but what is it in? It's in the D block,
10.
3D,
Oh my gosh.
and the first one.
Can you guys
Three D
add now?
And yes, and so Bryn's right, we can go 3D1, who would be 3D2?
Titanium.
3D3,
Vanadium.
vanadium, 3D4,
Chromium.
and who would be 3D10? Zinc.
What?
Wait, it's not manganese.
Wait, can you help?
3D10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Zinc. All right. Here's what I want to show you. All right. Because we talked about this before, like when was an energy level full and when did we start filling? So at 1s2, this is full, right? The first energy level is full.
Yeah.
What element is 1s2?
Helium.
Helium. Okay. Then we start filling the second level.
Oh wait, I know this.
Okay. Boom, 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 boom. At 2p6,
It's neon.
we're filled, and that's who?
Neon.
You see what's happening?
It's all on the edge.
We start filling. We're full.
All the ones on the very
Argon.
right.
And then we start filling it again. Okay. So do you see that in this configuration, we are full at which element?
At the last one.
Which is
in the
called
row.
the noble gas.
Yeah.
Okay, helium, neon, argon. Okay, so then after this, when this whole energy level is full, what element would we be at? Krypton. All right, so this illustrates the next way that we can abbreviate a configuration, because hopefully you see that as we go farther and farther on the periodic table, this is just going to get longer and longer and longer. So we need to have a way to shorten it to make our lives easier. Okay? But it's going to illustrate something. Okay? So how do we do that? Well, I was going to do scandium, because this is scandium, right? Okay. What's the noble gas before scandium? Argon. Okay. So I can just take all this and call it argon. Okay. And then what's left over? 4s2, 3d1. Okay, now, very important. What did Alpha say?
Electrons to the
Wait,
lowest
why did
possible
they
energy.
just put like what?
So, should I go 3 first or 4 first?
3.
I should do 3 first. I should do 3 first. Okay? So really I should go 3d1, 4s2. Okay. Now, for class, I would take either of them. Because one of them really is kind of right if we're using the periodic table as a map. Okay? But one of them is more correct because of the energy level. Okay. But do you see how we can use the noble gas to chunk all that together and then just communicate what's left over?
I have a question.
Question.
Why didn't you put, hold on. Vanadium because of the extra 2 for us. And then just put the 3D.
Oh, no, because, right? If I'm starting at argon, then the next element is in S, is in 4S. So 4S1 and 4S2.
Oh.
And then I go to element 21 with 21 electrons, 3D1. Okay. So, and hopefully all of you saw, like, when I came up and checked, what did I do? I just counted. So scandium should have 21. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Right? So you can always check. Just make sure. Not a common mistake, but a mistake that crept in last period. Would I want to go 1s2, 2s2, 2p6, 3s8?
You can't do that, can you?
I mean, there's an 8 there. Can I go 3s8?
No.
I gotta spread them out.
What are we
S2,
talking about?
P6. Okay, so we
Because
don't.
the 3, he
Don't
can't
wanna do
have 3s8.
Okay.
Why not? Because 6 of them are in P.
Because an S can only have 2.
Yeah. Because he said so.
All right, so here's what I want you to do. Take your element that you were working on and do the noble gas abbreviation.
Why does it say practice today?
Oh, look,
It's AR.
You do your abbreviation.
Oh my god, you cutie.
Just a limit.
Yeah, that's the,
I don't understand.
I don't either.
Okay, how do we do S2?
AR.
and then noble gas.
So it'd be
Is that right? Wait, explain. Go.
Because the last noble gas is argon, and then it goes down to potassium, and then there's only one in the
For sphere.
Or
that's
right
true.
closure.
Yeah. But if it was
Or elements of
for
calcium.
S,
Which
two.
is
Yeah.
left, you know?
Okay.
Do you see it?
At all.
Well, do you see it?
Yeah.
So you have to look at the last noble gas.
In that
So my
row.
sister.
No, in the row, like the row.
And this is
Yay!
So like calcium, because you're basically just taking
With the argon. So with the noble gas abbreviation.
jazz. So you're just
So you
What's the
go
noble
up
gas before 90?
one all the way to the right.
Carbon? No. Boron.
no, it's
Noble
and
gas.
then that's the noble
Carbon.
gas you have.
Neon.
No,
Helium.
Helium.
like so our row.
Okay, wait, now I'm really confused.
Because you can see it by the K.
Wait, what?
actually
Look at it.
And helium.
Is there a periodic
You
table?
only have 13.
Hey,
Someone did this.
so it would be.
Me.
No.
We're gonna put
The,
Zeros.
no, the,
Oh, wait,
no, the
wait,
extra, the extra.
I didn't have a-
Okay.
there we
You need 3, no, another 2 on P.
Are we right?
Oh, yes.
Oh, but how many are?
Oh, I forgot.
Yeah. You only have 13.
Yeah.
Oh, no.
I feel like they just started grabbing random stuff off the periodic table and realized this is probably cool. This looks smart.
Until I get to the noble gas.
And you put the two because it's
Helium
broken.
thing is just.
No, because it's
Okay, so then you make
the two electrons are not those above.
Yeah,
So that's why you use
I was just
4s1.
I think I will understand.
Yeah, no, it looks weird.
Like a
Are
white.
we gonna be response with the kick here onto the
Yeah, we'll go back to that too.
I love it. I'm good at them. They make me so smart.
I don't think
Neon, and then neon.
Can we sit down? She looks at me
It looks better than it did in my car.
Okay, questions on that? I think seeing your work, we're good,
Yeah.
I wouldn't say good.
but we're at the beginning.
I can maybe do the worksheet. I don't know about all that.
You want to mark back?
Yeah, go ahead and put your marker back on the tray.
King China. Loki,
All right, grab a seat and I'll talk to you about what we'll be working on.
This would be love. We're talking about. Have you ever ordered from Shein? Have you ordered from Shein? You should. I got my nails. I got this ring, and I also got it's all Shein.
Oh, so if you were doing a drip check, that's what it's called, drip check?
Yeah, like it's all Shein, and it's such good quality, and it was so cheap. It was like less than $20.
Okay, flip over to page 111.
What? I'm convincing him to buy from Shein. If you're gonna buy from Shein, you should buy my car.
I actually forgot to do one thing,
Oh, that's
but it's okay. So we can use the configuration to introduce a very important concept.
Yes.
Okay, and so we'll go magnesium, I'll write that. 1s2, 2s2, 2p6, 3s2. So this is magnesium. Okay. Now, in magnesium, what is the highest energy level?
3S.
3s. Okay. Highest. Okay. So then how would we describe everything else?
below 10 or 11.
Below it.
It goes up to 3S.
Okay.
I don't know.
Yeah. So notice there's this distinction between the highest
The lowest.
energy level and everything else that's underneath that. And we can see that in the diagram, right? So in hydrogen and helium, you know, they're kind of exposed. Is there any electrons outside that are kind of covering up stuff on the inside? No. Okay. But now when we go to lithium, the 1s energy level is covered up by 2s. Okay. Then when we would go on, and if we were to add 3s, now 1s and 2s are covered up by the 3s. Okay. So we can think that, you know, if we kind of relate that to our diagram, 3s is covering over everything underneath. Okay. The electrons that are in the highest energy level, we give those a special name, and I bet some of you remember that.
I remember writing it down.
Okay, valence shell. Okay. Valence shell being those electrons on the outside, highest energy level. Okay. Then everything underneath, we call that inner shell. So valence shell, inner shell. Why is this important? Because it is. Because when we start talking about chemical reactions being the interaction of electrons, which electrons are we going to be talking about? The ones in the valence shell. Okay? And so this is why the noble gas configuration is useful. What can we do with these inner shell electrons?
Like a mental, different.
Well, yeah, we can bracket them together and call them the inner shell. Who is 2p6? Neon. And then all we have to do is list the valence shell electrons. Oh my goodness gracious. In our configuration. If you remember back to freshman year, what's the maximum number of valence electrons we can have?
8.
Wait, what grade was that?
Did I guess right?
You guessed right.
I guessed right.
8.
What?
So 8 is the largest number of valence electrons.
Yay!
Okay.
Are we done?
Okay, questions on that? So on page 111, you can see that table at the bottom. They go through some of the configurations using noble gas configuration.
Yeah.
That's the noble gas configuration, and the one where you, oh yeah, the one where you put the noble gas, probably.
Yep, so this one's called just the electron configuration.
Can I look at it?
This one's called noble gas, which should make sense. Like, why do we call it the noble gas?
Because it's a noble gas.
Because we're using the noble gas to abbreviate. Okay.
Yeah.
And then this one, what do we call it? The arrow one?
Arrow one. Spin diagram.
Yep, spin diagram or orbital diagram.
Yay.
Because we're showing the spin.
Is that a 1 or
Yeah.
a 2?
See the time. Okay.
Okay, what's next?
So, starting today, working through Friday, because I'm going to be gone on Friday, you have the 2 worksheets to work on. Collaborate, work together, just like you did on the board, to work through those problems. You can do 2 first, you can do 3 first, however you want to do it. I'll just be floating around, answering questions, helping out.
Okay, perfect. And then I have a question. Yeah.